All right, good morning, everybody. Welcome back. Happy Friday. Today, our ninth class. You are hopefully currently working on project number 3. I know some folks have already made good progress on it. Not due for a while, but you have all the tools you need to complete that project if you have time over this coming long weekend. So we've got Saturday and Sunday off, but then Monday is President's Day. No day classes this coming Monday. Evening classes meet as scheduled Monday night. So we won't see each other again until Wednesday. Also due on Wednesday is going to be quiz number 3. I've just handed it out to you, so go ahead and grab a copy of it right now. The directions are written at the top of the quiz, but let's just make sure we're all clear on it. This quiz is a U substitution quiz. Only U substitutions on this quiz. 12 antiderivative problems, nothing more and nothing less. We recently saw this technique called integration by parts. You will not be using that technique on this quiz. Today we're going to have a new technique called partial fractions. You're not using that one either. It is just U substitution practice because U substitutions are critically important to us this semester. So in the directions at the top there, it says you can use a 1-page reference sheet of your own creation, and that is all. So that's the only resource you can use on this quiz, 1-page reference sheet of your own creation. I think it says scientific calculator too, if that's helpful to you, but this is not, open book, not open note, and you got to make sure that you make that reference sheet before you sit down and start this quiz, okay? No time limit on the quiz, but give yourself enough time to complete it without having to stress about getting it due on for Wednesday. Any questions on the calendar? So I mentioned we've got this brand new technique today called partial fractions. On Wednesday coming up, we're just going to kind of bring together all the different antiderivative techniques we've been talking about and give you some pointers as to when do you use each one. Like at the moment, we're just thinking about like how do you do the technique, and I'm giving you 20 problems in the homework where they're all used the same technique, but on the test they'll all be mixed up. And so we need some strategies for when do we try U substitution, when do we try today's technique, partial fractions, when do we try integration by parts. So we'll kind of bring things together on Wednesday coming up. Friday, 1 week from today, is our review for our first test, which is happening a week from Monday, 1 week from Monday. Okay, not too early to start studying. I gave you a whole separate packet of practice problems that you can use to kind of help you prepare for this test. Okay, so that's where we are and where we're headed. And let's take a look in the packet here. There we go. Okay, daily summary. In this class, we learn a new technique for integration called partial fractions. Number 1, let's find the integral of x plus 26 over 2x squared plus 5x minus 12, and then there's a note to me which you can ignore. Here's the idea. This integral right here, so we've got a couple of techniques for fractions, and none of them is going to work on this integral, but let's just try the few things that we do know about fractions. If I gave you, for example, x squared minus 5x plus 2 divided by x, something like that. You guys know the technique we can implement that will allow us to find an antiderivative? Not U substitution, not on this one. Not parts, not on that one, nope. Yeah, we're gonna make 3 fractions out of this one and then do some canceling. So this is really equal to integral x squared over x minus 5x over x plus 2 over x, right? So if you have like one term in the denominator, you're always welcome to split it up over the several terms that are in the numerator. And in this case, it gives us 3 integrals that we can do. And so we would just do them all separately. That would be the technique here. So certain kinds of fraction integrals, that's the idea. Then we have, I'm going to erase this in a second, and this one too, but then we've got something like this. So let's suppose at the bottom here is like 3x squared minus 7, and the top is 4x dx. This one we cannot split into different fractions. There's 2 terms in the denominator. But here, the denominator is decidedly more complicated than the numerator. And so if we try a U substitution here, what's a good guess for you? Is the denominator at 3x squared minus 7. And then the derivative of that is 6x, which looks an awful lot like the 4x that's up there. So you've got the same power. We can turn the 4 into a 6 without a problem. U substitution is going to work here. This integral is going to turn into something like 1 over u du. There'll be some other constants floating around. And what's the integral of 1 over u? Is ln of u, okay? So basically we've got two kinds of fraction problems that we know how to solve, but they're both very particular. Here it's got to be one single term and then we split. In the example in number 1, is it one single term in the bottom that we can split into multiple fractions? No, it's not that. The other possibility is that you let u equal the denominator and hope that the derivative is pretty much sitting upstairs. Okay, well we can try. If we let u equal the denominator, so if we let u equal the denominator, then what is the derivative? You don't need to write this because it's not going to work. Derivative is 4x plus 5. Okay, does that look like a multiple of what's sitting upstairs? Upstairs I have an x plus 26. I cannot just multiply that x plus 26 by some magic number and make it look like 4x plus 5. It's just not going to work. And so we've tried our two fraction techniques that we know so far, and neither of them works. And today we learn a brand new technique that handles this kind of fraction problem. So here we go. Let's first factor the denominator. I'm going to copy the original thing here. And I'm going to factor that denominator. So 2x squared plus 5x minus 12. In some previous math classes, you have a lot of practice factoring trinomials. So you're imagining two sets of parentheses all multiplied together, hopefully building 2x squared plus 5x minus 12 when we do all the distributing or foiling. The fact that it's a 2 in the front of the x squared makes it a little bit tougher than if it were just x squared. But let's just give it a shot. First terms have to be what to give you a 2x squared? It has to be 2x and x. That minus 12, that's kind of bad news for us. Why is minus 12 not so great?
There's a negative.
Yeah, there's a negative in there. What about 12 is like annoying? What if it were 7, I'd be a lot happier. There's a lot of factors of 12, right? Like we're just doing trial and error here, and until we get the right one, 12 has a lot of factors. Could be 4 and 3, 6 and 2, 1 and 12. And we just have to cross our fingers and hope that we can find the one that gives the 5x when we do the outers and the inners. Okay, let's just see if we can zip to the right answer. Anybody have a miracle here? Okay. So 3 and 4 we said was one of the factors. Leanna said it's got to be a negative and a positive. Let's just see if this happens to give the right thing in the middle here. When we do the outers, what do we get? 8x inners is minus 3x. And altogether, when we smush them, positive 5x. That's great. But you got to be able to have that miracle. You don't have to have it that quickly, but you got to be able to get there. Okay, so here's what I'm going to write. I should copy this. I'm going to write a over 2x minus 3 plus b over x plus 4. So a and b are constants that we're going to determine. So keep them as an a and b. I'll temporarily just put a couple of numbers here. I'll put a 2 there and a 5 there. Don't put the 2 and the 5. But if I asked you to add these two fractions together, what would we have to build before we could smush them together to make a single fraction? We need to build the common denominator, right? What is the least common denominator? Well, in this case, it's just the product of the two denominators that we have. So you can imagine, like you need to, let's go a different color here. Like you need to multiply this bottom by x plus 4, and so don't put any of this down. And so you have to multiply the top by x plus 4, and over here, what do we need to multiply by? 2x minus 3, and therefore the top by 2x minus 3, and now the denominators are the same, yes? And so if you add these two fractions, the lowest common denominator is 2x minus 3 times x plus 4, which is exactly the denominator that we've got over here. Now, if I distribute 2x plus 4 and 5 times 2x minus 3, I'm probably not going to get x plus 26 because I just made up the numbers 2 and 5. But would you believe that maybe there is some choice of those numbers that is going to magically give us x plus 26? Is that reasonable? Well, we'll have to do some algebra to find them, but that's what we're after. And so just thinking, just like looking ahead a tiny bit here, suppose that we do find those magic numbers, and I'll pretend for a second that they are 2 and 5. They're not going to be. But suppose that it's 2 and 5. What that would mean, don't write this yet either. What that would mean is that the integral of the original is equal to this integral over here. And that's got a plus sign, so we can imagine two separate integrals. And the integral of 2 over 2x minus 3, do you see the technique that's going to work for antiderivative there? It's going to be a natural log. We're going to let u equal what? 2x minus 3. And then the derivative is just plain old 2, which is a constant. Oh, great, I've got a constant up there. It happens to be the right constant, but any constant up there would be okay. It's different from trying to let u equal this denominator in the beginning, because the derivative of that denominator looks really nothing like what's sitting upstairs. But here, the derivative of the denominator looks like the thing that's sitting upstairs. So once we found the 2 and the 5, they're going to be different numbers. We're going to have two simple ln integrals. That's what's going to make this thing tick, okay? So that's sort of like the broad view, like kind of like here's where we're going. So really all that's left is the detailed, how do you find the a and the b? And that's going to essentially solve the problem for us. Okay, so I think we are here. Again, a and b are constants to be determined. Okay, so what we're going to do is multiply both sides of this equation right here by that lowest common denominator. So you should write this down. We're going to multiply by 2x minus 3 and x plus 4. And the same thing on the other side over here. Don't really have room to put this. So that's supposed to be on the left side of the equation. And then we get a brand new equation that's going to be much simpler. On the left side, the stuff that we just put up there in red completely cancels this denominator. That was the point. So we just have x plus 26 equals. The right-hand side is a little bit trickier, but we can handle this. So you're going to imagine taking all of this and distributing it to the two fractions that you see in here. When I distribute that red stuff to the first fraction, what cancels? 2x minus 3 cancels, and so I'm left with an a on the top and also the x plus 4. See that? So that's what we have here. A times x plus 4. Plus, see if you can write down the other part. That's this red thing distributing to this second fraction. Something will cancel, something will be left. You need to write down what's left. So what's left? 2x minus 3 is left. What else is left? The b, right? The b that was up there before is still there. And this x plus 4 will cancel, and you're left with just the other part, 2x minus 3. Okay, so we've got this brand new equation. It's got no denominators in it, so it's better for us. Some students try to jump to this equation, like from this thing that I've got bracketed first in red, and they just try to jump to this thing without really understanding, you know, oh, the a is with the x minus 4 or the a is with the 2x minus 3, and it's just a bad idea. I think it's much, much better to just take your time, write down this decomposition, we call it, and then multiply by the denominators. Even though there is a shortcut, you know, with a lot of practice, you can kind of do that shortcut, but still think it's worth writing, especially in the beginning here. It doesn't matter where a and b is. Let's suppose that that you didn't bother writing this thing down and you just jump to this guy. And suppose that we end up getting a is equal to 2 and b is equal to 5, the numbers that I got before. If you put 2 and 5 on top of the wrong denominators, you're going to get the wrong integrals. So it doesn't matter here, but you got to know where they came from. Oh, wait. Okay, here we are. All right, so we've got this equation. How many letters are in this equation? 3, A, B, and X. And we're trying to find A and B. X is a variable and A and B are constants to be determined. It's not necessarily really clear what we're after. This is sort of a strange looking equation. Like if I say solve that equation, well, what am I really asking you for? What I'm asking you for are the particular values of A and B. Maybe A is 2 and B is 5. But if I'm asking you to find A and B, typically you'd need 2 equations, right? Not just one. This equation has 3 letters in it, not just the 2. Okay, so here's the twist. This appears to just be one equation, but actually this equation is supposed to be true for every value of X. Any value of X is supposed to make that equation true. Any value of X is supposed to make the original equation true. So what that means is that we can pick any value of X that we want and get a new equation which won't have an X in it. So I'm going to make up 2 random-ish values of X. Any X that you want, I don't know, I'll pick X equals 1. And then I'm going to rewrite that equation right there, but change all of the X's to 1s. On the left-hand side, 27 equals. On the right-hand side, how much is in the parentheses? 5. So I'm just going to write 5A. How much is in the parentheses? -1 over there, right? X is still 1. So this becomes a -1 times B minus B. And that is starting to look a lot more familiar to me in terms of like past algebra classes. That's an equation that I can, like if I had another equation that looked like that, I could solve for my A and B. How did I get X equals 1? I just picked a number. You can pick any number you want to. X equals, Jake, 10. Just plug in X equals 10. You can't go wrong here. On the left-hand side, 36 equals 14A. And there, careful, it's some 10, right, 17, B. Okay. And this system of equations is one that you have solved, like stuff that looks like that many times, okay? So you take this kind of unfamiliar looking, what do I do with all of this? And you turn it into 2 very familiar looking equations, right? Pick any X's that you want to. Okay, so now we just have to solve. There's a couple of techniques. We're not going to do them both here. You could do the method of substitution, where you solve one equation for one letter and substitute that into the other letter, right? Or you could do the elimination method, also called the addition subtraction method, where you try to make it so that the coefficients of like let's say the coefficients of the B's are the same, but maybe the opposite sign. So like if I multiplied the first equation by 17, then I get -17B here. And if I add, that's just going to perfectly cancel. But you got to multiply everything by 17. So 17, 17. Either technique is okay. Let's just do substitution here, but really you can pick. If I solve this equation for B, I'll move the B to the left and bring the 27 to the right. So we go 5A minus 27. It's okay. And then we substitute that into the other equation. 36 equals 14A plus 17. And then instead of B, 5A minus 27. And how many letters are in that equation? Just 1. So we keep making these equations better. Okay, so let's solve this thing here. 36 equals 14A plus, what is that? 50, 30, 85? Minus. I feel like I should be able to do this guy. 23. I'm not going to try. What do we get? 17 times 27? 450. What is it? 459. Okay. All right, and then we smush some A's together. So we get 99A equals, and we move that 459 to the other side. 495. Is that okay? And then divide both sides by 99. And once we know that A is 5, how do we get B? Plug that in. I think the best place is right here. Just change the A to a 5, and that gives you the B. B equals 5 times 5 minus 27. Is that negative 2? So A is 5 and B is negative 2. Okay, so we've done a lot of work on this one. The fact is we haven't done any calculus yet, so we still have to do the calculus part. But to be honest, the calculus is simpler than this algebra technique that we've applied here. I don't have any space here. Is there room on the bottom of this page? What's going on down there? There's some room down there. Okay, so let's jump to the bottom here and say that that original integral is really equal to, and now we're going to have our two simpler fractions. So we figured out that A was 5, so the first fraction is a 5 over, and then this is the part where we got to make sure we put the right denominator. Was it 2x minus 3? And then the other fraction was a negative 2 over, I'll write it as just a subtract 2 over x plus 4. Is that right? Okay. I'm going to leave some blank space for that first guy and do the second one first. Minus 2. This is basically a 1 over x plus 4. So that was going to become an ln, right? That's a natural log right there. So it's ln of x plus 4. I'll put absolute value. If you put parentheses, that's fine. And that 2 is just pulled out of the front of the integral. The other guy, it feels like it should be the same technique. So what comes out of that first fraction? Just the 5 initially. So we got a 5 initially. Then it's going to be ln of 2x minus 3. And it seems like that's the answer. That's our pattern. But the fact is that's not the right answer. It's close, but it's not complete. We're not going to do all the details here. But we had said that we should really be doing a u substitution here. What's the choice for u on the first fraction? 2x minus 3. And when we do the derivative, we get 2. And you have to pay for that 2. And so I'm just going to, like, without writing all the details, say ... But you're going to end up with a 5/2, not just a 5 on that one. You got to go through all of the details there. I'm hiding them, but this is a full-fledged u substitution you got to do here at the end. The second guy is okay, but it's just like sort of a coincidence that we got lucky on that one. If you let u equal the x plus 4, what's the derivative? 1. So technically there's like an invisible divide by 1, but who needs to write that? Okay. All right, questions on that? Okay, so let's look at some stuff in general about this technique. Again, it's called partial fractions. So here's the idea. The form, the decomposition of a rational function into partial fractions takes depends on the factored form of the denominator. In our case, our denominator became 2x minus 3 times x plus 4. So any factor that you have that just looks like an x minus some number, like an x plus 4, x minus negative 4, you just put a number on top of that thing. So a over one of them. It was actually okay that there was a 2x in the front of ours. Anything linear becomes a number on top of that factor. A over one of them, b over the next one, c over the next one if there were 3 linear factors. But I distinguish linear factors from quadratic irreducible factors. So for example, something like that, we can't factor that thing, right? X squared plus 9 cannot be factored. We factored our denominator, but x squared plus 9 we couldn't. And so if you get a quadratic that is irreducible, not factorable, you do not put a number on top of it. You put a linear thing on top of it. You put an ax plus b on top of x squared plus 9. And if I had another one, it would be a cx plus d on top of the quadratic. So any quadratic needs to get a linear thing on top. We'll see a particular example right down below. The only other thing we have to contend with is repeated factors. If you have x minus some number to a power, then you put a over x minus the number plus b over x minus the number squared plus c over x minus the number cubed plus all the way to the end where you finally build up to whatever power you had at the start. So let's see all of those together. I think it'll be more understandable when we look at a concrete example. So take a look at this guy. The numerator makes absolutely no difference. It's the denominator that we focus on. I see x minus 1, I see x plus 1 squared, and I see x squared plus 4. X minus 1 is a single linear factor. It gets a constant on top. So that, let's see if we can highlight some stuff here. This guy leads to a over x minus 1, and it's done. The next guy is this x plus 1 squared. It is a repeated linear factor. It's squared. So what you do is you put a letter on top of x plus 1 to the first, then you put another letter on top of x plus 1 squared. If it had been cubed in the beginning, you'd have another letter on top of the thing cubed. So you just build up starting from the first power all the way up until the power that you have, okay? And then finally, x squared plus 4, can't factor it. It is irreducible. It doesn't just get a number on top. It's not just a d over. It's a dx plus e. It's a full-fledged linear thing on top, okay? Those are the only 3 kinds of things that you'll ever have to contend with. Okay, on the next page, it says we're just going to set up this one. We're not actually going to do the antiderivative, but we'll set it up. Okay, so again, ignore the numerator, just start with the denominator. I see x squared plus 1 and x minus 2. Let's write the original fraction here just so we've got it all out. Okay, x squared plus 1. Does it get a constant on top, or does it get an ax plus b on top? It gets an ax plus b. X squared plus 1 is an irreducible quadratic, so it gets an ax plus b on top. I'll do the same highlighted thing that we did before. And that guy's done, okay? Plus x minus 2. Does that get a c on top or a cx plus d? Just gets a c. And that one is done. That's how we set it up. Then we got to do lots of algebra to find the particular values of a, b, and c. And then finally, antiderivatives. That's not what we're going to do right now. You'll have a chance in the activity, but that's the setup. One last look at our calendar here before you jump in the activities. I mentioned we had integration by substitution, huge technique for antiderivatives. Last class was integration by parts. Today is partial fractions. Next class will kind of bring it all together. We do have one more integration technique right after the test called trig substitution. Partial fractions and trig substitution are the most challenging of the antiderivative techniques that we'll see. The fact is we can type in just about any antiderivative we want into Wolfram Alpha and it will spit out the answer more quickly and potentially more accurately than any of us can do. Part of what we're after here is the idea of how do antiderivatives work, and let's recognize that the more we know, the more we realize we don't know. And also maybe a sense of appreciation for the folks who did all this before they had Wolfram Alpha and the lengths to which they had to go to find antiderivatives. And these are like the most elementary techniques we could find, and there's tons more that we're not going to cover. So this is really an opportunity to think back to our forefathers and mothers and the calculus stuff that they had to go through before they had the technology that we have today. Okay, so the activity is right there. I will walk around.